Table-driven logic is a technique where we use data to replace complicated logic. It can be a really powerful technique for building clean code that is really easy to modify. Pretty surprising for complicated logic. To set this up, let's think about an example where we're building a portion of a system that is supposed to translate error numbers to error messages. The code to do that might look something like this. Not too bad, but imagine a real system where there are hundreds of error messages. And if we wanted to handle errors, this code could get a lot more complicated. And then, what happens if we want to internationalize and translate to other languages? My first fix to this is called a direct access table. We just put the messages into a table that is indexed by error number. Our code is simpler, but the real power of this is that we could choose to read the table from a file. That's where things get cool. Now, we have one file for English, one for Spanish, one for Korean, and so on. Our code doesn't have to change at all. We change languages by changing which file we read. And one step further, if part of our system adds a new message, we don't have to rebuild the code of this part of the system. We just have to update the data files. Bottom line, putting the data into a file, we have delayed the binding time to runtime. That gives us better flexibility. Click above if you need a reminder about what binding time is. For our next technique, let's think about building a really big system built by a set of development teams. Then, how we allocate error numbers becomes an issue. We can't have two teams using the same number for different messages. So, let's make it easier and allocate a range of numbers to each team. We let them allocate within their own range any way they like. They just have to give a mapping of error number to error messages that they want. This works really nicely, but it has the side effect of causing lots of error numbers to not be used. That means our direct access table will have lots of empty spaces. As an alternative, we can build an indirect access table. We build one table that holds all of the messages compactly, and then an index table that maps error number to the index of the matching location. The code for using the table is still pretty simple. We just have one layer of indirection. And we could still read the tables from disk. So if the table is sparse and is larger than the index we add, this can significantly reduce the amount of memory that the tables use. This also has the advantage that if the data we're storing was complex and we wanted to index by different aspects of this data, we could build multiple index tables into one shared data table. The downside to this is that keeping the tables in sync is pretty risky. You can see that adding a message requires that we add it to the data table and make the right index table entry contain the new position. That's pretty fragile. So I like to embed the key into the table and search the table instead of indexing the table. I've created a class that holds the error number and the message associated with it, and I've built a table for those entries. To get the messages for a particular number, I just have to walk through the table looking for the error number, and when I find it, the message is right here. Yes, this is going to take more runtime, but it's much more robust than the indirect access table because the error number and the message are right next to each other. And I can add new ones to the table anywhere I like because the order no longer matters. Even though I've hand-built the table, we could still read this data from a file, so I can still deal with internationalization at runtime. However, the one downside is that I've had to duplicate error messages where two error numbers cause the same error message. One more step to go. Suppose that instead of just finding an error message, we wanted to attach a behavior that can handle each message. In Java, we can put those behaviors into different classes that all implement one interface. Think strategy pattern. Then we can put those behavior objects into our table. Now, instead of just returning the error message, we can execute the handle method on the behavior object. So We've embedded behavior into our table, and that's a lot cleaner than it would have been if we had embedded the behavior in the original switch statement. Check out my video on function pointers to see how we can do that in C. Bottom line, table-driven logic embeds different cases into a table so that we don't need complicated conditional statements. There are a number of options for how we can design those tables, and choosing the right one depends on memory space requirements, runtime requirements, and maintainability requirements. Please like and subscribe. It helps people find these things.